Welcome back, everyone, to another HyperSDK Developer Community Call. Super excited to see you all again. This call is mainly going to be focused around state key management, as this has been a hot topic in the group chat and on the HyperSDK repo. So I will hand it off to Patrick to kind of like lay the foundation of where we sit at today and kind of lead the discussion around what we could decide.
Yeah, before we do that, I wanted to call out a cool showcase project that Minaj, who I'm not sure is here right now, was playing around with. So I'm going to drop that here and share my screen real quick. So funny enough, he got interested in the exact same thing I saw and also got interested in, which is that there was this discussion on the Celestia forums about using snarks as like accounts on chain. So folks that are close to the HyperSDK know that we're working on like a programs capability, as well as working on like an EVM capability for the HyperSDK. But a totally different route to go is instead to like treat accounts just as snarks and then encode arbitrary logic inside of the snark that you can use for any of this. And so Minaj saw the same forum post I did, apparently, and thought that was cool, and then actually ended up implementing the entire capability using the action auth flexibility of the HyperSDK. So you can generate a proof, some circuit, and then use that to then secure funds using the auth module. So if you want to run through it yourself, I mean, this is obviously pre-audit or there's no warranty on this. I'm not super familiar with some of the ZK primitives, so I can't attest how correct it is, but super cool. I think when I see stuff like this, it's a great reminder that at least some of the core abstractions of the HyperSDK seem to be flexible enough for most of even use cases that I hadn't really considered, which I think is a good sanity check. So happy with that. But yeah, so we had been talking in the Telegram group where some people had asked some questions about state keys, and particularly the state keys in the multi-action world and how you can kind of connect state keys together. And so before we get started, I feel like I should just give a quick reminder of state keys and what they are, why they exist, and just to set the stage before we kind of get into a discussion of what we should do with them. I did not write a section about them, it seems. So I will go into then. There's an issue that Aaron created that talks about them a bit. And I will drop that here. Okay. So when we were working on the HyperSDK originally, one of the things that we saw to be a very early bottleneck was, things that I think other people have also seen pretty clearly is first the how long it takes to fetch keys from disk that are used in execution, and then secondly, executing all transactions in serial. So the highest performance way, regardless of DX, to do this is to just require every transaction to explicitly specify the keys that it's going to need. And so if you do this ahead of time, you can make sure that you have enough funds to fetch the key, like fetch whatever keys are required, go fetch those keys, and then also trivially parallelize execution, because again, you know exactly what state every transaction is going to touch. Now, other networks and like projects have taken a different approach where they've tried to introduce something called optimistic concurrency control, or I think Aptos has branded it block STM, which does not require developers to explicitly name all the dependencies of their transaction, and instead the engine will handle that for you, where in the worst case, it may execute the same transaction multiple times. I think at worst 2 if it's parameterized correctly, if I'm not mistaken. The benefit of this is that you as a developer don't need to care, like whatever happens with your execution happens and the engine will handle it. The worst case, again, is just that you end up having to do more execution or fetch keys kind of out of loop if like there's some conflicts in the block. The other downside of maybe the state key approach is that if you have like a lot of conflicting state that's interacting in some way, transactions can easily invalidate each other. So if I think Dariush, you played around with this a bit with the EVM stuff and saw this as well. When you name state keys, let's say in like a traditional EVM contract world, if those keys change or like there's different dependencies or branches that get hit based on previous transaction interaction, your transaction will just get immediately invalidated instead of gracefully handling potentially like dependent conflicts across transactions. But from a pure efficiency perspective, like explicit state keys seems to be the most efficient, but it ends up being like a question of your definition of efficiency. Because if you have these like canceled transactions because of state key changes or like your execution starts to touch other state keys, then you might have issues. Now, I don't think I myself haven't run into this much because like most of the implementations of actions that are explicit, meaning there's no like program or smart contract component to them, are pretty straightforward. Like you don't even have to explicitly name the state keys. You can just derive the state keys from whatever the action is. But when we get into a world of like supporting smart contract functionality, you pretty much have to provide a list of state keys that are going to be touched, which I think is something that the EVM also considered doing at some point, and I think Solana also does, which people have loudly complained really impacts the developer experience. So that's the setting the stage component. And I think what maybe a good example of what this looks like is if you go into the examples, we'll use a complicated one because that's more interesting. Let's just say like create order. So you can see when I'm creating like this order on the exchange, like I'm saying what the ratio is for trading in and out, and then the amount of tokens I'm locking up. You can see that the state keys I've specified are my balance, and then the order key that I'm creating with specific, basically access control rules, or like what I'm going to do with this key. And that's how you also get charged. It's based on what things that you require each state key to do. But you can see when I'm creating the transaction, I don't have to like specify them. I just specify like my action, and then I can populate the state keys from that. But in the world where like you don't have that, like let's say it's just like a call into some top level function, you end up potentially having to do a lot more work to get that information. So I know Steven also had a lot of thoughts on this at different times. I don't know, Steven, if you want to chime in on anything. I saw you just hop in and out. I'm assuming you went in some elevator or something.
Yeah, I think that the question is just kind of like where we expect like hyper VMs to go, right? So I personally find it pretty unlikely that we're going to get to a point with the state key approach that people will be happy with the UX in an EVM world. So like if we want to just take EVM contracts off the shelf that people have built for things like ETH mainnet or other EVM chains, like maybe the happy path here is there's going to be an additional 20% key failures, but like if people start hitting the same contract all at the same time, like that could spike, especially depending on how like that contract is implemented. So like I feel like the state key approach is great for things developed for hyper VMs, but I just don't know like like I certainly don't personally have conviction that it'll like work well for like an EVM put on top out of the box, right? And so at that point, like if that's a direction that we think is important to go for like early adoption of the Hyper SDK, then it seems like this is going to be something that either needs to be configurable or like this isn't like super workable. Like that's basically my concern. I'm super interested to hear on like developers that are like actually like looking at building out stuff on the Hyper SDK to like what their thoughts are on this. But yeah, that's kind of my like concern succinctly, I would say. There's a lot of pros, by the way, that like if we like on either side, we can kind of take the design really far. But this seems like a kind of an important decision.
For example, like one of the things that you can do by taking it far. So as we've discussed previously, this mechanism VRIX will be integrated with the Hyper SDK, which will allow us to really push the throughput. That's what that like demo we gave was, where we move into more of like a DSMR world. In that world, execution is not happening prior to block packing. So like when like chunks are created, we don't execute anything yet because we don't know the state over which to execute it. In a world where we have state keys, we know how many state keys are going to be touched, and like that may allow exactly which state keys are going to be touched, which may allow us to do certain tricks when we're packing the chunk. You could ahead of time understand like the concurrency of the chunk, for example, which you could potentially like depending on how the fees work there, may offer or change the fees in a way that makes the network more robust. If you don't have that, you end up having to, you don't know what keys you're going to fetch ahead of time. And as a result, you may end up, it may be less efficient, or like you may have to do some weirder fee stuff where like you can't actually fetch stuff ahead of time because you don't know if people will actually be able to pay the fees to cover all the like things you're going to fetch. So there are non-trivial trade-offs here in the implementation world, especially when we start to talk about like decoupled state machine replication steps. So state keys for that work really well, in my opinion. In a world where you don't have that, I think it gets a lot more complicated.
Would love to hear like maybe some people that are like developing on the Hyper SDK where their thoughts around this whole state key management stuff is right now.
Or we're just down. Yeah.
Yeah, I guess I'm a bit confused about the other approach. You said Aptos was doing something like that, and Solana. Could you go into a little bit more detail about how that would work?
Yeah, Solana also does explicit state key management, so it's similar to what is here. It's not quite the same, but has the same idea. Aptos and I think Monad as well is also pursuing this as a different strategy, which is typically referred to as like optimistic concurrency control. They have branded that block STM. I'll drop it in as well, so you can just follow along. The idea with that, in a nutshell, is that you naively or like optimistically execute everything, assuming that there are no conflicts with any of the transactions. You probably don't run ahead super far in case there are conflicts. So like maybe a few ahead, or there's a lot of heuristics you could tune. But you execute optimistically, and then when you have like a follower pointer, let's say, that locks in the result of that execution. And when you get to a transaction where you determine that the execution happened with a certain view, but that view was updated prior to the execution of that transaction, or like what would have been the execution of that transaction, because remember the results you have to be deterministic. What you will do is then re-execute that transaction on the proper state because it may have changed the execution output. So the way it works is you just basically assume you're good to go, and then you try to fix stuff later via re-execution. Now, the theory or the idea is that most of the latency for execution there is actually in the fetching of keys from disk. And so most times when you re-execute the same transaction, the keys will probably be in the cache in some way. That's not guaranteed. Like the execution could change based on the value of the state key, like that is pulled, or like whenever it's executed, or based on some value. But in theory, most of the time. And so a re-execution, especially if your virtual machine is tuned for like very high throughput, should not be very expensive. Like any single transaction execution should be pretty quick. So the theory is that that is good enough. Like the extra gas you get, or like, I'm not going to use gas because that's going to confuse everything. The extra like power you get from having like a much more strict state key management ends up being not as crazy. But you can see that, like, at least in their paper, they talk about how when there are like non-high conflicting workloads, it gets up to reasonable numbers. But then when you have a super contended workload, it comes down quite a bit because of all the retries. So the alternative in the HyperSDK, or like where you have explicit state keys, is that they just like kind of queue up. And that's not to say that in the explicit state key world that the performance would be necessarily any better, because you are blocking in the case where you have conflicts. But it's unclear without some more work, like how expensive this like retry capability is. Now,
I think like my main detractor for the optimistic world is actually that you are executing this transaction before you're prefetching. So you still have that like kind of jittery, like you start executing the transaction, you hit some like DB read that you haven't like seen before, you block on that DB read, and then like you get that value and then you proceed. And then, in the world that you have to retry, okay, fine, maybe hopefully everything's in state now or in memory now, maybe some things aren't, whatever. But like that's actually like the concerning thing that I have with the optimistic route, because in the state key, pre-specified case, you can just right at the beginning start fetching all the things that you need. And so you never have this like kind of like depth of execution reads, which like sequential reads, all your reads are parallel.
I think the other thing that is what I was always attracted me about it is that you can be very clear about like the resources that any single transaction can consume. So like in this world, you could have the same transaction fetch not unbounded number of keys, but a lot of keys. And so let's say that you're like doing the optimistic execution. You're like, okay, this person specified like a multi-dimensional fee of this much. I'm going to go fetch this many keys and then stop. Now you have to re-execute it. And then as a result of the re-execution, because of some branch in the logic, they now fetch a whole set of different keys. Like there is some extra fetching that could occur as well that makes it tougher to bound potentially like the fee that they're being paid. And so really the VM eats the extra cost instead of the users eating the cost. But yeah, the DX stuff is understood. So I saw Patrick type something before you raised your hand, Martin. Do you want to ask that? My preference is always to go to Patrick's first. If not, I'll just read it out. So the concern that Patrick has is that state keys work fine when you know prior to the execution of the action, which the state needs to be modified, but you cannot at the moment change the state key permissions during the execution of the action, which would be limiting for certain use cases. Example, modifying the balance of an address that is not known at the execution of the action. So I think this was... Yeah, so I mean, like if you don't know what route the thing is going to take until it's executed, or like it's equally likely it could take one of like N routes, it's very difficult. And I think that's maybe a reflection of, at a high level, of like the EVM case we discussed. I think the other thing that we talked about was this whole like multi-action thing, but I don't want to bring that quite in yet on some of those like abstract action IDs that we talked about. But yeah, I think that is the main thing there. Is it like pushes more onus onto, like pushes more weight onto the application developer to design an action interface or like a contract interface that works well with this idea that you have to specify state ahead of time, which I know in other ecosystems that require this, people have complained quite a bit about. Martin?
Yeah, I think it goes into that example and what I suggested in the group, kind of like that we are, like just specifying a very large number of state keys in our transaction, because from what I understand, I will only be charged for state keys that I actually read or write to. If I don't do that, I won't be charged for it, or my transaction won't be charged for it, right? So in this example of the lottery, if the participant set isn't too large, I could like literally specify all the participants in anticipation that I may change all the balances, but then actually, like, obviously only the winner will be changed. And was wondering if that's kind of like one workaround for a better DevX, like just be very generous with the state keys you specify. But then on the other hand, if there's no cost to it, also maybe we can touch a little bit, is that in somewhat a danger, right? Like, let's say, like there's like a popular DeFi protocol and someone just always specifies the state keys even though they're not planning on touching it, but then kind of like creating a bottleneck around that one.
Yeah, so there, this has been changed. So like with Vrix, you pay for every key that you specify. And then if there are read conflicts, both go through. But if there are any like write conflicts, they won't. So there's still a question on your second part around like an attack surface. You can still kind of grief a bit if you like name a bunch of read keys because it's cheaper to access, and then that would limit someone from executing a write key, but you would still pay for that, but less than the amount that someone's going to try and pay to write. Now, that doesn't necessarily get away from the problem, because in like an optimistic concurrency control case, you could just iterate over like a bunch of keys and cause like a bunch of other transactions to get re-executed. So like it's not like a silver bullet or you get away from the problem by switching. I think the one thing that a lot of these systems haven't quite nailed yet is how to charge for causing serial execution in a deterministic way.
I see.
But that's so to me, that's something that could be done, for example, in the pre-specified state key case based on each chunk. So like, because all the state keys would be known ahead of time, you could easily know like what we would call the depth of your chunk is. So we could just say, hey, like you can't create a chunk with depth more than 3. Straight up. Like you have to be sequencing highly parallelizable loads. And so you don't put that like weight on the users, you just require that for a chunk to be semantically valid. But if you don't have keys like that, there's nothing you can do if like the dynamic, like if the execution is fully dynamic.
I think one other thing I wanted to ask in that, because I understand now we have these different state keys, right? Like read, write, like, and I think allocate and some others. And something that came to my mind also thinking about this example of the lottery is, for example, like changing a user's balance. What we will always have to do is for, like, if we had this large number of state keys, which is not in the picture anymore because of RIGs, because we're getting charged for it, but let's say we have a large number of state keys and I want to modify balances. I was like, okay, we always have to specify read because we need to get the current balance, and we need to specify write because then we like change the balance and thing. But from a developer experience or efficiency perspective, maybe I don't really care about what the balance is. Let's say a user has 10 and I want to increase it by 5. I don't really care if the user starts at 5, 10, or 15. I just want that after I can modify the balance so it has 5 more at the end. They win the lottery, they get 5 tokens or something. So I was wondering if it just didn't come up, or if it was a conscious decision against, like something maybe like a modify state key, where I specifically don't care about the value, so I'm not reading it, but I'm just modifying it. So kind of like, like the value it is today plus 5, or whatever, right? Like this kind of idea.
So that gets kind of complicated. You can do that for commutative operations, right? So like, plus ignoring like, well, if you account for like overflow, whatever, plus is like a commutative operation, as you said, right? Like if I do like 5 + 3 or 3 + 5, it doesn't matter. I get 8 + 8 at the end of the day. The thing here is that generally, like, you don't know the operation that's being performed. So even if your operation might be partially commutative, right? Like I'm doing a +5, which is a commutative operation. Someone else is doing a like ×2, which is also a commutative operation. But together they are not commutative, right? Like, and so you need to kind of be like very specific where like the actual like engine understanding the conflicts has to know whether or not it can safely do like an atomic update. And so that's yeah, that's where the complexity comes in. But definitely it's possible to do this, but yeah, that's the
Yeah, I think the
the tricky part.
complexity comes into overflows. Like
Even
like
overflow is technically fine if it's deterministic, right?
fair. I think like because the case that solves, you could argue is like the NFT minting case. I think is what usually people talk about. It's like, oh, I want to mint. Like there's 1,000 people that all want to mint the same NFT. Like parallelism does nothing for you there. Like what you really want is more granular or like commutative kind of transaction support or something. And then what you come back to, and this is where it just gets complicated. I'm not saying it's impossible. Is that like, oh, let's say there's only 500 to mint. How do you execute things in parallel, but then still enforce that constraint? So stuff to consider. So I think we had talked about this at one point of like adding a special type of state access key where you can like kind of do this in a cool way where the engine itself will handle the counting, which should be a lot faster than like anything else handling the counting. So it will feel more parallel, I guess, but yeah, we haven't implemented that yet because then this whole question of like the state key approach being the right approach came up quite a bit. Another point that someone brought up from, I think, Frederick here was it pushes the cost off chain because you need to fetch all those keys. Yeah, I mean, I think this really just turns into a question of like in the generic execution case, like it's way tougher. In the actions built for the HyperSDK route, it's, in my opinion, almost always derivable from the action itself, and none of that fetching actually has to happen. So, yeah, I think another route we had. Go ahead. I don't know if you have anything else you want to add to that.
No, I'm all good. Thank you.
Another route we had talked about was making this part somewhat generic or like open and letting you do either or. So like not maybe at the same time, but something where like the HyperSDK could have different modes based on like your application that you wanted to launch on the HyperSDK. But my fear with that is that if we're trying to get to a production launch, having like this, Rubik's Cube of combinations you can play with seems to just like there's gonna be a bug. So like I feel like we can't accommodate that from day one. I think we need to pick an approach. Now, I think the other thing that we mentioned was some of the data model that we've been playing, or like database we've been playing around with, somewhat may change the calculus. So I don't know, Stephen, you brought that up if you wanted to touch on that.
I'm not sure that I brought it up, but I can definitely touch on it. So there've been
Vilma
some.
was your idea, right?
Definitely not the name. Anyway, but yeah. So with the Vilmo kind of idea, essentially, if you look at LSM databases or B-tree databases, whatever, just key value stores. ignoring Merkleization, ignoring anything else. You have, both read and write amplification, right? So what that means is that when I write a key, I'm actually going to be performing, some number of disk reads or writes more than one, right? So that's the amplification factor. So oftentimes this never ends up coming out to be like 7 writes or something along those lines. And similarly with reads, like you're not actually going to get like a single like DB read. You're going to have to traverse some form of tree in order to perform your read. Now, of course, on the read side, you can cache things. So maybe you don't have to hit that every time. And internally, you might have some of the levels get cached, what. Vilmo is implemented in a very different way, where it essentially says, well, rather than trying to support pretty efficient writes and pretty efficient reads, we are going to support super efficient writes and like no support for efficient reads. So when you do that, you say, okay, well, I can write with like a single DB write. That's great. Problem is, okay, well, I actually need to read this data. So we kind of fall back to that caching approach and saying, well, you can just cache this stuff. But if I have a cache miss in Vilmo, I have this very expensive DB read. So rather than doing actually caching, Vilmo will explicitly keep all of the keys in memory explicitly. Now, there's been a bunch of work to see like if there's ways to like optimize that. But like as far as the base Vilmo kind of like idea, the keys are in memory. Now, this is super fast for obviously like accessing a key, it's already in memory. Writing stuff is a single DB write, which actually makes it so that the state key like pre-specified beforehand maybe makes less sense or is at least less of a requirement for high performance nature, because if you're doing these random reads, it's actually not that slow anymore because you're not hitting this like deep accesses into disk. You're actually just essentially already in memory. So in the Vilmo world, if you're okay with having a much higher memory requirement, like you end up essentially getting reads for almost for free, right? Not for free, but like not significantly more expensive, not on the orders of like hitting like DB reads. So if we were to go the Vilmo route, as far as state goes, the prefetching is less of a concern. Now, currently with like HyperSDK, it uses MerkleDB, so it's the Merkleized like Patricia or like radix tree. So you aren't going to necessarily be able to prove like individual key value pairs and things like that as easily. It's probably not that much of a concern. Vilmo still supports state sync, so if we were to push on like we need this super high levels of throughput, and Vilmo is like the database that provides that, then at least from the actual execution time, it seems like the state keys are less required. Now it's still maybe important for like parallelism and like managing parallelism, things like that. But as far as the actual like raw time it takes to execute transactions becomes less important, in my opinion.
Does anyone, I actually had a question. I don't know if anyone expects to generate proofs over the state of like a hyper VM. Silence is assumed to mean probably not, but curious. Most people that I've seen like interested in it from a roll-up case are like running roll-ups separately that they want to generate proofs over, but not the actual state that's persisted to the HyperSDK, and they're using that more for like some sort of DA thing or like shared sequencing thing. The only thing we've thought of, I guess Michael thought about it. I'm not sure we want to talk about that here yet, but some cool stuff you can do if you do have state proofs across different subnets.
Yeah, I feel like that'd be a pretty large tangent from this.
Yeah.
I'm not entirely sure what part of the state you need to prove for given use cases.
Yeah.
So
I think even with Vilma, which doesn't have like state root generation on a periodic, like on a per block or even like a built-in basis, like I think you could still generate like trees and then include them somehow. But like that just seems like if it's not in like if you want to include it in consensus or like have everyone agree to it, like having some sort of like out of band protocol, I think could be a little difficult. But I think it would be possible using like some multi-signature BLS thing. But I think some of this decision seems to be born from deciding how we want to do or like what path we want to commit to on the data management side.
Yeah, I mean, the Vilmo question is very concretely, in my opinion, like
the thing.
What is the memory like footprint that we're expecting to enforce people to have for the HyperSDK? Because like in the traditional world, you can optimize reads by just like bumping up your caches, right? So like you look at the C chain, you can change a config and bump up your caches, just like change a number in the state, and like it doesn't really impact people that much. It enforces all the same rules. It's just, with a higher number, if you have more RAM, you can execute faster, right? So it's kind of like more flexible. Whereas in the Vilmo approach, like you need, in order to be able to like process things with any reasonable performance, you need to have the keys easily accessible. And so like that is going to, very much impose like some relatively high base RAM requirements. So like, is that a problem? Depends on the use case.
just going back
to be clear, that's just the active state size. It's not like any sort of historical revisions of the active state. It's just the number of existing keys to execute the next state transition. Michael?
I was just thinking about it a little bit more as far as wanting to verify proofs about the state of another chain in a cross-chain sense, and then being able to import certain events that have happened. I'm honestly not yet convinced that you need the state root. It could very well be something more equivalent. I think this might have been what you're alluding to, Patrick, of like the receipts root. Since it's just the current, like the state of that block, it's subject to change in the next block anyways. So really, if you're looking for a specific event that occurs, it doesn't necessarily need to be touch state, I guess. I'm not fully, don't have full conviction behind that statement, but yeah, just wanted to call it out.
Yeah, Dariush?
Yeah, I mean, now that we have the community on the call, I think maybe one question that when looking at the storage trade-offs is like how many or like how much state do people actually require if they have like a generic smart contract chain? And also what type of like validator requirements are people comfortable with? Because these two parameters, as Stephen was talking about, determine like how much RAM we have and how fast eventually things can go. Also, like another useful data point to know would be like what size of values people are interested in storing. So another trade-off that one could consider is that we allocate larger chunks of memory to the programs, and then the programs kind of manage that memory themselves, as opposed to like the EVM level where it provides these granular 32-byte keys and values. So any input here is helpful.
Arish, I think it'd be helpful to like maybe give like a tiny quick overview of some of the sizes of memory you were talking about that we've had conversations about before.
Well, for example, I'm thinking that like we would consider like 32 gigabytes of RAM for validators kind of like standard at this point, but maybe 64 is kind of getting a bit more expensive, especially if we like allocate, 16 gigs of RAM for just like indexing state keys or something like that. There's other caches, operating system caches, consensus caches, etc. But this is kind of sort of the numbers where my head is at least. But definitely any type of feedback here. I don't know if people are perhaps comfortable with much more larger numbers, or they just don't have that much active state to begin with, or are perhaps comfortable in getting larger machines as their state grows.
AWS, for what it's worth, does have a node that goes up to 24 terabytes of memory. So in case anyone was curious, you can get pretty big here. Only for $218 per hour. So the infamous U class.
What's the price? What's the price at 64 while you have this set?
It always depends on like number of cores you do, but you can get pretty reasonable with that. That's the on-demand price. So if you're going to run a validator, you probably would be doing the reserved price.
I guess another idea while you have this tab open, Patrick, is a lot of AWS and cloud storage, they have network-backed storages, which are like persistent when you turn off your validator. If we do go the route of requiring a hard, like high-speed, like NVMe present for validation, that kind of changes like the operational aspect of things a little bit as well. You'd have to like manage your own backups and stuff, as opposed to just like detaching the volume. Maybe you wanted to highlight that high class of machines that are available for this type of work.
Yeah, there's always like a middle route, I think, for this, which is to use NVMe drives instead of RAM, which are a lot cheaper to acquire. And then there are like, to get it up to a speed where it's interesting, we have found experimentally that you need to go with these i3 style instances, which give you really quick access to NVMe drives. i4 now, sorry. But yeah, I think the story probably comes from some of that. So I think like what I really wanted to convey during this community call is there are a number of different levers kind of that when pulled in different areas, like make things make more or less sense in different directions. And I think for the HyperSDK to be initially successful, it has to have like some great initial like use case. And so, for example, in like a basic trading or like collab world, you can do this without any optimistic concurrency control, and like it would be really fast with state keys and Vilmo. Like you could do so many orders per second. Whereas if we moved into this world where it's just like a little bit, I guess, more pessimistic or optimistic around like the execution of what we want to do, it may open the door better to like smart contracting at high throughput, but will make each invocation arguably less efficient unless we do like state keys there, which make the user burden heavier and may require you to like put a bunch of extra bytes in your transaction, which is just naming all the state keys that you're going to touch. Unless you like rewrite Solidity contracts or something like that from scratch to try and best align with the parallelism. But like it gets tough because you're just not in as much control with the Solidity compiler and like how it lays out certain variable access. Whereas like in the HyperSDK programs, you have a bit more control. So I think you could probably be better there. But how good at databases do we want the average app developer to be, I think is the question. And like how optimized or like tuned will hyper VMs get? from the perspective of like really being tailored for a single use case, or are they going to try to be like general computation machines?
One question I have is like, so most of the code has, state keys specified everywhere right now. So like we're trying to get like the V1 that we feel comfortable with, like the fastest turnaround with that is almost certainly going to include state keys. How complicated would it be to just allow the database backend to be configurable? So either essentially a Vilmo or a MerkleDB. Because it seems like Vilmo, it incurs this like big memory footprint, which I'm personally concerned about. And it seems like if you could just like pick those and it isn't like a substantial overhead to like the code base, like code structure, like we already have, like MerkleDB is going to be included into the, broader Avalanche ecosystem as time goes on, almost certainly, right? Like, so that's going to exist. If MerkleDB, or sorry, if a HyperSDK ends up like putting time into like fully speccing out and implementing Vilmo, then that will also exist. So like, we're definitely going to have MerkleDB. We might have Vilmo. Does it make, like, how complicated would it be to let the creator of the Hyper VM pick which one of those is the kind of backing?
I'll share some code while I walk through it. So the way that it works for the most part is in the chain itself. I'm sharing the wrong page. In the chain package itself, there are dependencies. One of those dependencies is on, wrong folder. So the state requirements, like that the HyperSDK is aware of, are here. So like when you basically operate over either immutable or mutable state. So, and a mutable state is services, like the immutable or fulfills the immutable interface. So as long as any database pretty much meets these, you can use it. The part that is less generic right now, but will become much more generic with bricks, is the view thing, because views are no longer going to be used because execution will only be asynchronous. So you'll just need to basically return some sort of like checksum, root, or whatever you have that has an ID by some point. So to answer your question directly, plausible for sure that you could choose, like the database implementation part could be left open and up to the implementer to decide how they want to actually store and manage state. There may be some like optimization parts that we need to think through, like where there may be more than one hook to like how you want to, like, oh, do you want to fetch anything? If so, this is your fetcher versus like a different type of fetcher. But given that there's probably there's like a bifurcation of demands on like whether or not you want to have more memory or less memory, like it definitely makes sense to me that you would keep it open for both.
I mean, there's going to be more things than this, though, right? Like you have like how you, like the state sync mechanism is going to have to be different.
That's true. So maybe it wouldn't be fully exposed, and you would just have like a mode you could pick, and then that mode could never be changed, or something like that. I think the thing that, upon further reflection, I like a lot about Vilmo in like this memory-focused world is that the accesses in are all the same speed. You don't have to worry about cache misses. Whereas if you're at like, so like if we try to target execution time to be like, 1/50th of the block interval, if there's cache misses, probably be okay, maybe. But if you have like a ton of transactions and all of them are cache misses, like the variability of your block execution time can be dramatic. So having everything on the same plane will allow you to arguably like have a higher throughput, I think, like a higher safe throughput, which we come back to, I think, as the purpose of the HyperSDK. Like, is it to be like a super generic builder kit for any virtual machine you want to build on Avalanche? Or is it meant to be like the high throughput one? In which case, I'm sorry, we're using memory. Like, I'm sorry, it's using state keys. Like, you want high throughput, this is going to be safe high throughput. And then over time, we loosen some of those constraints. That would be one way I think you could go about it, rather than having it be super loose, being unreliable, or have like very variable performance, and then try to tighten those constraints to say, oh yeah, that one was too loose. Like, we got to reel that in. And so I have personally taken the approach, given, you know, our experience of like running different Avalanche validators as well, said more to myself, I'm interested in this like very tight operating window where like if there's a way to constrain it, let's constrain it and then loosen it if we get comfortable. Also, because the constraining usually makes the implementation simpler, in my opinion. You just have to have like a lot of those heuristics.
I know we've talked at length about this kind of stuff in like DMs and directly, but like I think there's no doubt Vilmo's gonna be faster. I think the question is like for HyperSDK, like is the goal for HyperSDK to target the highest performance VMs, or do we want to be able to support VMs that do not have such high throughput requirements? Like, do you need to have 100,000 TPS on your chain for it to be useful? If the answer to that is yes, then like ditch MerkleDB, ditch like, you know, typical LSM trees. You got to use Vilmo. Like I think that's where, you know, we're at from a development standpoint. But you know, if you want your Hyper VM to have 20K TPS with reasonable memory requirements, Vilmo is probably not ideal. So that's kind of where, and again, this is like simple transfers or, you know, micropayments, whatever, when I say TPS. But like, so that's kind of where I'm at. Like, you know, I feel like most people probably don't need stupid levels of throughput, even though like that is very much the goal of like HyperSDK is to enable stupid levels of throughput.
It sounds like you're talking about HyperSDK -slow, the repo.
I mean,
I think
it's actually it's like HyperSDK like cheaper is actually
or like
what I'm
OK
like,
SDK or like
on sale.
SDK. Yeah,
It's the HyperSDK on sale. You know, it's the meme of like, you know, oh, like mom said we had like, you know, burgers at home kind of vibe. You know, like that's
the value SDK. Yeah, that's a good one. I think like to round out this point, there's typically like quite a strata of it seems like when you're at levels of throughput, like some of these design decisions like change quite a bit. So like if you're trying to get from the 0 to 100 range, the 100 to 1,000 range, the 1,000 to 10,000 range, and the 10,000 to 100,000 range, there seem to be different design trade-offs that make sense, which offer the best user experience or like developer experience. And so if we're targeting the HyperSDK as a whole, which has been the goal to like the performance is our North Star to hit that difference, would be this 10K to 100K range. Like there are just decisions that had to be made that to make that stable that unfortunately will impact some developer experience, but it will give you that stable performance.
which is why I'm very interested on how easy it would be to make them pluggable and decide. Because if it's like easy enough, right? Like again, we already have MerkleDB. Like if it's like, and we already have like state sync on MerkleDB. We already have like the MerkleDB stuff is already in and done, right? So like if there's a way to basically make an option to just switch out and say, okay, instead of MerkleDB, use Vilmo, you know? like then like I'm down, you know, like because at that point you're good.
All right, so there's a few comments here. So Space Devox, the time between getting live and researching these problems is large. Totally agree. Feels to me the important thing is fixing the interface to enable these options being explored once use cases come online. I think that makes sense. Like I said, I think starting with a constrained thing and then making it more flexible over time, to me, is the safest way to do it, where we're still guaranteeing progress. Hopefully that constrained interface services like enough user needs that it's interesting. And then someone else, Samuel, do you want to say this out loud, or do you want to, I can read it. I'll read it. For our use case, speed would be far more important. If you want slow generics, you've got EVM. We would easily notice the difference between 20K and 100K TPS. So, I mean, I think it's just, to me, it's about finding your niche and like your set of explicit trade-offs that differentiate you. And I'm not sure how differentiated, or like it becomes much harder to clearly differentiate ourselves if we're playing in the like up to a 10,000 TPS game, given all the stuff coming down the pipe.
Yeah, I mean, I think to be clear, like I'm not advocating for a, hey, we had this Vilmo idea, we shouldn't do it, like because it imposes too much. Like I think that we want Vilmo just for like the max high throughput case. Like, because again, HyperSDK is targeting to have max throughput, but Vilmo has some very specific trade-offs, which are definitely not ideal for everybody. And again, HyperSDK isn't meant for everybody. But the question is, who is HyperSDK meant for specifically? Like, is it meant for just the people that need the highest throughput? I don't know. I think realistically, like, you know, HyperSDK is the most polished kind of like toolkit that like the Avalanche ecosystem has for building VMs. And so in the foreseeable future, if someone is trying to build a new VM, they will be building it on the HyperSDK. And so like, this is, you know, very realistically the space of VMs that are going to be built out in the Avalanche ecosystem for the foreseeable future. So like, if we are constraining it to only being, you know, Solana-esque hardware requirements, then that is kind of the short-term future, short to medium-term future for Avalanche subnets outside of subnet EVM kind of instances. So I think that's, you know, that's those are the thoughts going through my head on this decision.
So that was a long conversation around that side of trade-off. The other thing that we're also working on, which I think will make the pre-program use case super interesting, is this thing about multi-dimension, like multi-actions and outputs, which some people had also called out. So this, for example, for like a trading use case is critical. And so in the trading use case, like you may want to set up multiple orders or like do multiple things and then only succeed if all of them go through. And so this is one of the bigger PRs that gets us closer to like integration ready interfaces, which allows you to, let me see if I can pull up an example of doing this, but yeah, this will be a good one. We'll let you string together multiple actions with a single authentication, which I think for a lot of folks is going to open up the door to quite some interesting stuff. Let's see if we can pull up one. Yeah. Should have this example ready. Create order. Should be right around here. So like here's an example where you can do two transfers in the same action. They only succeed if both go through, or like you create a bunch of assets. They only succeed if all of them are created. or like mints, or like, oh, you have to create 2 orders, like you're trying to take a certain position. It only succeeds if both go through. And you can do all of this without any like generic like execution engine. So this can be super optimized, and then like you basically take the union of the state keys that are required for each action. And so you can do some really crazy stuff, which seems like you would need to have like contracting to be able to do. And then I think some of the Swissborg folks call that like, you know, you may want to string these things together, like do something based on the first action. And so that led me to the idea of using this abstract action ID, where each one of these will have its own ID. And so if you want to reference it, you can include like a certain formatted ID here, which is basically all zeros with the action ID that's being referenced. So like the order ahead of you. And then at compile time or like execution time, those zeros will be updated with the actual transaction ID that's being run so that you can execute. So like you could create an asset and then mint it in the same transaction, which would be kind of cool. So I think with that gets us pretty close to having like these like non-generic execution use cases that would be pretty powerful to get going. So, but the question is if the HyperSDK just becomes just really good at trading chains, in which case is that the goal or not? But in a heavily financialized like application, it becomes kind of interesting.
Can you explain a little bit more about that? It's like zeros replace thing. What is that?
Yeah, so the action ID here, that's like the base identifier for everything in the HyperSDK is 33 bytes. The first 32 bytes are the transaction ID, and then the last byte is the like basically the index in the action array. My idea to allow people, so in some cases, you have, let's say that this was a create asset and a mint asset here. You need to name the ID that you want to use for the mint, but you don't know it here. So how do you specify it? You want to have some like special ID, in my opinion, to allow you to like somehow name some previous action ID as the ID to use for this argument. And so one way you could do it is just treat the TX ID of all zeros as like a special ID, which gets populated in the execution to be the TX ID that's referenced.
This is like action specific. Yeah.
Very action specific. Yeah. It's more of a program, like a developer experience thing, not really anything special. Yeah. But yeah, I think on the development side, like the goal is to get to this integration ready checkpoint soon, or that's like the first step, so that people can really start to get into the virtual machine building side of it while the under parts of the HyperSDK are hardened. So that would mean that the like VM experience is more or less full, and then underneath it will be optimized and hardened to get to production. But anyone building a virtual machine should be able to do that with confidence that whatever they write should be overwhelmingly close to what they could actually deploy when the HyperSDK is ready for production use. So that's the current plan. So once this is implemented, I'm going to make some changes to the fee accounting and then the RPC module, which are VIX compatible. And then at that point, it should be ready to utilize really to start to harden the virtual machine side while the HyperSDK makes more progress. Cool. Well, I think we're about 7 minutes over, so I'm not sure if Jacob, you have anything you want to wrap up with?
No, sounds good. We'll post the call after, and then I think Patrick kind of mentioned this in the group chat, but we're really trying to focus all the conversation and discussion into the open. So please, if you have questions, like small questions, feel free to throw them in the Telegram group chat. But any like bigger discussions, especially around the state key, let's try to keep it on the GitHub so people can follow along and join it.
Yep.
Sweet. Have a great day, everyone. Thanks for coming.
Thanks.
Thank you. Bye bye.